In this module, we shall learn about continuous probability distribution and its various types. Continuous probability distribution can be categorized into different probability distributions according to its theoretical approach. In this module, we would be focusing on the following. Number 1, normal distribution. Number 2, uniform distribution, and number 3, exponential distribution. The graphs of the above distributions are symmetric and are useful in predicting the likelihood of an event within a certain range of values. All the above distributions are parts of theoretical continuous distributions. We will start with the concepts of continuous probability distribution and then talk about the three theoretical distributions mentioned above.
After studying this module, you shall be able to know the concept of higher order derivatives. Know the various applications of higher order derivatives. Now, let us begin with the second and higher order derivatives in detail. Given a function y is equal to f of x, its derivative with respect to x, that is dy by dx, is called the first derivative. Since dy by dx is also a function of x, it can be differentiated further. The derivative of dy by dx with respect to x is termed as the second derivative of y, denoted by d of dy by dx whole upon dx is equal to d square y upon dx square. Proceeding in a similar manner, we can obtain the third derivative of dy by dx, that is d cube y upon dx cube. Fourth derivative d4y upon dx4, going till the nth derivative dny upon dx to the power n. The first, second, third, going till nth derivatives are also denoted by f dash x, f double dash x, f triple dash x, going till fnx. Let us now focus on derivative as a rate of change. The derivative function f dash x measures the rate of change of that function f. By the same token, the second derivative function f double dash x is the measure of the rate of change of the first derivative f dash x. In other words, the second derivative measures the rate of change of my original function f. f triple dash x measures the rate of change of the second derivative f double dash x. To put it differently, with a given infinitesimal increase in the independent variable x from a point x is equal to x0, f dash x is greater than 0, meaning that the value of the function tends to increase. Similarly, when f dash x is less than 0, it means that the value of the function tends to decrease. Whereas with regard to the second derivative, f double dash x greater than 0 means that the slope of the curve tends to increase, and f double dash x less than 0 means that the slope of the curve tends to decrease. The sign of the second derivative is related to the curvature of the function y is equal to fx. When d square y upon dx square is greater than 0 over a domain or its subset, the curve is strictly convex from below, and when d square y upon dx square is less than 0, the curve is strictly concave from below. If d square y upon dx square is greater than equal to or less than equal to 0, the function is said to be weakly convex or concave otherwise. It may be pointed out that the condition d square y upon dx square greater than is not necessary but sufficient for convexity, and if it's less than 0, it is not necessary but sufficient for concavity. Now let us study how the second derivative affects the shape of the graph or curve. The figure shows a concave curve in which at different points on the curve the sign of the first derivative, that is dy by dx, differs. At points on the extreme left of the curve, the first derivative is greater than 0 as the curve is rising initially. Then, at a particular point A, the first derivative becomes 0. This signifies equilibrium position, that is, a point where there is no further tendency to change position and the graph is neither increasing nor decreasing. So, when we take points ahead of the equilibrium point A, then there is a tendency for the graph to fall, and the first derivative is thus less than 0. This graph represents all points where the second derivative is less than 0, that is, negative value d square y by dx square can be associated with negative, positive, or 0 value of dy by dx. The figure shows a convex curve in which, again, the sign of the first derivative varies at different points on the curve. Here, at points on the extreme left of the curve, the first derivative is less than 0 as the curve is downward sloping. Then, at a particular point A, the first derivative becomes 0 again. Now, as we move further, there is a tendency for the graph to rise and the first derivative is thus greater than 0. This graph represents all points where the second derivative is greater than 0, that is, a positive value d square y upon dx square can be associated with negative, positive, or 0 value of dy by dx. Application 1. The two curves above exemplify the graphs of quadratic functions which may be expressed generally in the form of y is equal to ax square plus bx plus c, where a is not equal to 0. From our discussion of the second derivative, we can now derive a convenient way of determining whether a given quadratic function will have a strictly convex U-shaped or a strictly concave inverse U-shaped graph. Second derivative of quadratic function cited is d square y upon dx square and is equal to 2a. This derivative will always have the same algebraic sign as the coefficient a. Positive coefficient gives rise to a U-shaped graph. A negative coefficient for a leads to a strictly concave curve shaped like an inverted U. Application 2. Diminishing marginal utility. Suppose Ux represents the utility that a person gets from consuming X amounts of good X. If Ux is greater than 0, then more of good is preferred to less of it. If Ux is less than 0, then every additional unit of the good generates less additional utility for the consumer than the previous additional unit. Application 3. Diminishing marginal productivity. As a firm increases labor input starting from low levels, its production capacity generally increases. However, the increase in productive capacity as more labor is added tends to get smaller. That is, the rate of increase in productive capacity falls as more labor is added. The graph clearly shows units of labor on the x-axis and total utility on the y-axis. Here, we represent the firm's production function by F of L, where L is labor input. Now, when we increase labor from 100 to 101, productive capacity might increase by 10 units. Further, increasing labor from 101 to 102 might increase productive capacity by 7 units. That is, the rate of increase in productive capacity falls as more labor is added. We can impose increasing productivity by requiring the condition F-L is greater than 0. We can impose diminishing margin productivity by requiring the condition F-L is less than 0. Second derivative test for relative extremum. If the value of the first derivative of a function f at x equal to 0 is f dash x0 is equal to 0, then the value of the function at x0, that is f of x0, will be first a relative maxima if the second order value at x0 is f double dash x0 less than 0, and a relative minimum if the second derivative value at x0 is f double dash x0 greater than 0. This test is more convenient to use than the first derivative test because it does not require us to check the derivative sign to both the left and right of x0. Nth derivative test for relative extremum of a function of one variable. If the first derivative of a function fx at x0 is f double dash x0 equal to 0, and if the first non-zero derivative value at x0 encountered in successive derivation is that of the nth derivative fn x0 not equal to 0, then the stationary value fx0 will be a part, a relative maxima if capital N is an even number and fn x0 is less than 0, b part, a relative minimum if n is an even number but fn x0 is greater than 0, and c part, an inflection point if n is odd. It should be clear from the preceding statement that the nth derivative test can work if and only if the function fx is capable of yielding sooner or later a non-zero derivative value at the critical point x0. Now, let's start with the topic of the Jacobian matrix. The Jacobian matrix is the matrix of all first-order partial derivatives of a vector function. Taking a function f Rn Rm, which takes as input real n tuples and produces as output real m tuples, such a function is given by m real valued component functions f x1 going till xn and fm x1 going till xn. The partial derivatives of all these functions with respect to the variables x1 going till xn, if they exist, can be organized in an m by n matrix, the Jacobian matrix J of f, as follows, where J consists of rows tending from first derivative of f with respect to x1 going till xn and columns where the first derivative of f1 with respect to x1 is taken till f of m. The matrix can also be denoted by Jf x1 going till xn and del f1 till fm upon del x1 going till xn. When m is equal to n, The Jacobian matrix is a square matrix and its determinant, a function of x1 going till xn, is the Jacobian determinant of F. The Jacobian determinant is sometimes also called as the Jacobian. Let's begin with the topic of Hessian matrix. Let z equal to zxy be a real function of two variables with the first order derivatives zx equal to zy and the second partial derivatives zxx, zxy and zyy. Hessian determinant H is a determinant composed of all the second order partial derivatives with the second order direct partials on the principal diagonal and the second order cross partials of the principal diagonal. The second order direct partials on the principal diagonal and the second order cross partials of the principal diagonal are represented in a Hessian determinant, where H is equal to first row consisting of second order partial differentials with respect to x and y, and columns consisting of second order partial differentials with respect to x and y, where zxy is equal to zyx. Now, let us study the second order conditions for a minimum. If the first element on the principal diagonal, the first principal minor, H1 determinant is equal to zxx is positive and the second principal minor H2 determinant is equal to zxx into zyy minus zxy whole square is greater than 0, the second order condition for a minimum are met. When h1 is greater than 0 and h2 is greater than 0, the Hessian determinant is called positive definite. A positive definite Hessian fulfills the second order conditions for a minimum. Here are the second order conditions for a maximum. If the first principal minor h1 is equal to zxx is less than 0 and the second principal minor h2 zxx into zyy minus zxy square is greater than 0, the second order conditions for a maximum are met. When h1 is less than 0 and h2 is greater than 0, the Hessian H is called negative definite. A negative definite Hessian fulfills the second order conditions for a maximum. Given y being a function of x1, x2 and x3, the third order Hessian is given as H is equal to, for the row, the first second order partial derivative of f with respect to x, then y and z, and for the column, all second partial order derivatives of f with respect to x, where the elements of Hessian are the various second order partial derivatives of y. y11 is equal to del square y upon del x1 square, y12 is equal to del square y upon del x1 del x2, y23 is equal to del square y upon del x2 del x3, etc. If h1 is equal to y11 greater than 0, h2 is greater than 0 and h3 is equal to h greater than 0, where h3 is a third principal minor, h is positive definite. The second order condition for a minimum are fulfilled. If h1 is equal to y11 less than 0, h2 greater than 0 and h3 equal to h less than 0, h is negative definite and second order conditions for a maximum are fulfilled. Higher order Hessians follow in analogous fashion. If all the principal minors of H are positive, H is positive definite, and the second order conditions for a relative minimum are met. If all the principal minors of H alternate in signs between negative and positive, H is negative definite, and the second order conditions for a relative maximum are met. The Taylor's formula which is used uses higher order derivatives, which can be seen in the formula given below. Taylor's formula fx is equal to f of 0 plus f dash 0 x upon 1 factorial going till nth derivative of f0 into x to the power n upon n factorial plus 1 upon n plus 1 factorial into f to the power n plus 1c into x to the power n plus 1 for some number c between 0 and x. L'Hopital's rule. If f and g are differentiable at a, with f of a equal to g of a equal to 0 and g of a is 0, then f of x upon g of x is equal to f dash a upon g dash a. If f dash a upon g dash a also turns out to be an indeterminate form, we can apply the rule again. That is, we will find f double dash a upon g double dash a and then solve for the limit. Application and repeated application of the rule often converts an indeterminate form to a determinate form, allowing easy evaluation of my limit.
Let us now summarize what we have learned in this module. In a uniform distribution, all the values of x within its interval are equally likely. The normal curve is also referred to as the normal curve of errors. This is because whenever x is the sum of true value plus a very large number of small independent errors, each equally likely to be plus or minus, x will be distributed in the normal distribution. The exponential distribution describes waiting time between Poisson's occurrences. The maximum value of the cumulative distribution is 1, and after that the slope of cumulative distribution is always 0, that is, within increase in the value of x, there will be no change in the value of the distribution function.